Take good care.
We can start. No, that doesn't work. You see, I'm a very bad chair.
All right.
We should start.
Okay, let's get started. So I was very unhappy to learn yesterday that the Unruh effect is not going to save us from the inevitable cooling of this room. So first of all, are there any questions from last time? Good. Okay. Everything's totally clear. All right. So, okay, what did we do last time? So we defined these topological surface operators, which are just the path integral language for conserved charges, as integrals of the stress tensor. And these are topological whenever epsilon is a conformal Killing vector. And okay, so this gave us the conformal algebra, which had some interesting commutation relations, and I'll just rewrite the most interesting ones. So the commutator of dilatations with momentum is I times momentum. D with k is minus ik, and k with p is a linear combination of dilatations and rotations. And using the conformal algebra, we derived the action of the rotation generators and translation generators on local operators that transform in a representation of the Poincare group. So this was minus I x mu d nu minus x nu d mu minus s mu nu O of 0, or sorry, O of x, where S mu nu is a finite dimensional representation matrix for the representation that of SOD that O transforms in at the origin. And I'm suppressing the indices. So you could imagine O has spin, so it carries some SOD index, and then this is a matrix acting on that SOD index. And this just followed from the Poincare algebra. And also as an exercise, I gave deriving the following. So the action of the dilatation operator on O at some point x is given by the conformal Killing vector corresponding to dilatations plus this intrinsic quantum number, the dimension of O. And I gave a physical argument that delta should be positive. Otherwise, you violate cluster decomposition. And we'll be able to do better than that argument, hopefully today. Okay, so good. So what's next? Well, we haven't used all the symmetries of the theory yet. So far, we've just used Poincare symmetry and rescaling to classify the operators. So the next thing we should look at is the action of the rest of the conformal generators, namely k mu on operators. And the first thing to notice is that k mu, so these are conformal representations. First thing to notice is that k mu is a lowering operator for dimension. So in particular, if you have some operator O at the origin with some dimension delta, and we consider k mu acting on O. So again, here I'm using this shorthand notation where the action of a charge on a local operator by a commutator is implicit. So in a particular quantization of the theory, this just becomes a commutator. In path-integral language, again, you can think of it as having the operator O sitting at the origin and one of these surface operators surrounding it. OK, so we have this. What is the dimension of this thing? So now we can use the conformal algebra. This is a commutator of d with k mu plus k mu d. O has dimension delta. So this thing gives I delta times O. This here we use that commutation relation. And the result is I times delta minus 1 times k mu O of 0. Okay? So if O had dimension delta, then k mu O has dimension delta minus 1. And so this means that by starting with O and acting with k a bunch of times, we can arbitrarily lower the dimension of this operator. But I said that dimensions should be positive. Otherwise, you could have correlators of local operators that grew with distance. So this process had better terminate at some point. Okay? So this means that there exist operators such that they're killed by k. So these operators are called primary. And given a primary operator, we can.
You want to equal 0 there, Dan?
Thank you. Good. So these are operators that live at the bottom of this kind of chain. And given a primary operator, we can form descendants by acting with momentum generators, or equivalently taking derivatives. So derivatives of an operator O at the origin, that's equivalent to just acting with momentum a bunch of times. And these are called descendants. And they have dimension delta plus n, where n is an integer. It's just the number of times that you act with p. And an example is the operator O of x, which is the exponentiation e to the minus I p dot x acting on O of 0. Again, here I'm using this. This is more of a path integral language where you have this surface operator surrounding O of 0. In the quantization, I would actually have a conjugation of O of 0 by this thing. Okay. This, by just expanding the exponential, is linear combination, an infinite linear combination of descendant operators. Yes. So I'm going back and forth between these two types of expressions. Okay. Well, one way you can think about it is when I write a commutator, I'm telling you what to do in a particular quantization of the theory. where O is a quantum operator and K is a quantum operator, and I'm saying you should take the actual commutator of them. And when I'm using the shorthand notation, you can think of it as what you insert into the path integral. Yeah, that's right. So yeah, a primary operator satisfies this, and if I sandwich it in between some arbitrary state, I still get 0. You seem unsatisfied with this notion. It doesn't matter. The operator is annihilated by K. So, I mean, yeah, we'll do some computations like that later, where some states are annihilated, some states aren't, and you'll see sort of how it plays out. But this is true in any state. Other questions? Okay. Good. So I know this shorthand notation has been causing some confusion. So would you like me to talk about it a little bit more in more detail, or are people mostly comfortable with it? A few words. Okay. Good. So let's see. So there are two equivalent notions. So there's this notion of inserting things into the path integral. So you could imagine that we're integrating over some field phi, and maybe O of x is phi of x, and then we insert some operator, some charge q, which is just the integral of the stress tensor. And when I write q phi, you can think of it in terms of just this picture. And in this language, these objects are just they're things you insert into the path integral. So you put this in the path integral, and then you sum over phi, and you just literally do the sum weighted with these quantities. Okay. In terms of the Ising lattice model, you can think about computing expectation values as spins, and the spins are just numbers that are plus or minus 1, and you're summing over all of them. Okay. And there's another way to think about this, which is in terms of operators and states, where now you have some Hilbert space. You start with a vacuum state, and your Hilbert space is it's some vector space. And now all the numbers you can insert into the path integral become reinterpreted as quantum operators on this Hilbert space. So sometimes people put a little hat on top of the operators. Okay, so this means you have a vector, then you act on it with a matrix, then you act on it with another matrix, and so on, and you take the inner product finally with some vector. Okay, and these give the same answer, but they're different languages for interpreting the computation. They're different ways of doing the computation, basically. And I'm maybe being a little cavalier about going back and forth between them. The claim is that, so I should finish writing this expression. The claim is that these two pictures are equal. So here in the path integral, we insert some stuff in the path integral. We do the sum over all the fields. We integrate over one of the points, and we get some number. Here we start with a state. We act with phi of x, which is a matrix. We act with q, then we take the inner product with another state, and we do it in the other order, and we subtract. And then these two things are numerically equal to each other. Okay? And when I write, when I just go back and forth between these notations, I'm dropping the hats, and I'm not specifying how I'm actually quantizing the theory. I'm not specifying where the spatial slices are. And the reason is because all the equations I write involving these commutators hold in any way of quantizing the theory. Okay. Did that generate any additional confusion? Yeah. Good. So charges become commutators. The natural thing for exponentials of charges to do is act by conjugation. So if you exponentiate e to the I times this, well, let me be very explicit. I'm talking about operators, which are matrices in some Hilbert space. So basically what this means is that the meaning of this is as a Taylor expansion, where you do 1 times phi plus commutator of q with phi plus commutator of q with phi, and so on. So this is e to the I q phi of x e to the minus iq, as you can verify, exercise. Okay, so basically what's going on here is elements of an algebra naturally act on operators by commutation. Elements of a group naturally act by conjugation, like this. Okay, so in path integral language, here we have some charge which is supported on some surface, and we can compute the exponential of that with 5x. In path integral language, what this means is we do a sum where we just do the path integral with 5x, then we do the path integral with phi surrounded by a surface q, then we do the path integral with phi surrounded by two surfaces q, and so on, and we sum. Okay, so that's the meaning of that. And these two different ways of doing the computation give the same answer. So in the shorthand notation, when I just write one of these guys, I'm just thinking you can just think of that in terms of the path integral language, but it means in the quantization language it means this. So basically it's a question of algebra versus group and how they naturally act. Good, you're jumping to the punchline, but yes. Okay. More questions? Okay. So exercise. So we've now said how k acts at the origin, and by doing a computation similar to what we did in the last lecture, you can derive using the conformal algebra how k acts away from the origin, and it has the same sort of structure as before. There are intrinsic terms associated with the intrinsic scaling of the operator and the intrinsic spin of the operator, and then there's the action by the conformal killing vector corresponding to k. Okay, so this is something that this before was just minus what I called little k. So this is a computation that you can do. Just as a summary, and I should say that this computation contains the action of k on all the descendant states of O. Okay, so we can consider descendants given by just acting with a bunch of momentum generators, and if you want to know how k acts on those states, you can just Taylor expand this whole thing in X to the appropriate order. So this packages together an infinite number of computations that you might do to find the action of k on descendant states. what that means is that once we've specified how k, d, and m act on an operator at the origin, we've now specified how all the conformal generators act on O and arbitrary descendant states built out of O. Okay, so we had these conditions that d with O at 0 is I delta O, m mu nu of O at 0 is minus s mu nu O of 0, and then k kills O at the origin. And this defines a primary operator. And given a primary operator, we can build a whole conformal multiplet off of it. So we have O, we have a descendant of O by acting with momentum. We can act twice with momentum, and so on. And these states have dimension delta, delta plus 1, delta plus 2, etc. And this is all we need to figure out the entire action of the conformal group. So for example, k, you'll find, takes you down in this staircase. And then here it just gives 0. And delta, d, and m just take you, keep you at the same level. And this is a conformal multiplet. And you can play around just using those conditions. Everything, the action of all the charges is completely determined on this space. This might look a little bit familiar to you. You can think of this as a lowest weight representation with respect to dilatations. We start with an operator that has a minimum eigenvalue with respect to d, and then everything else is built by using raising operators from there. And it's very similar to the construction of irreducible reps of SU2, where there you start with the highest weight, and then you act with lowering operators to generate the whole thing. And because you know you have a highest weight state, you can figure out, using the commutation relations, how everything acts on every state. And this is exactly the same construction. Later, we'll prove that all operators, all local operators, are linear combinations of primaries and descendants. Okay, so here I just introduced this multiplet by saying, hey, there should exist operators that satisfy this, and hey, we can then figure out the action of the conformal charges. But in fact, this will be all we need.
Question?
Yes?
So I assume algebraically we could introduce something with a highest weight state that goes down forever instead of going up forever. Do we just throw that away on physical grounds?
So for now, I'm throwing it away on physical grounds because it would violate cluster decomposition. Hopefully, by the end of this lecture, we'll be able to throw it away on more rigorous grounds. So it's basically a consequence of unitarity, or in Euclidean language, what's called reflection positivity. Other questions? Okay, good. So we've used the conformal algebra to classify local operators in the theory. And we now know how they transform under all the conformal generators. And a useful thing to do is exponentiate all of these actions and figure out how an element of the conformal group, which would be an exponential of conformal charges, acts on the operators. So we can consider some u, which is the exponential of some conformal charge. And we want to know how u acts on an operator O. So what is this? And by the way, in a particular quantization, this would mean, where we're being totally explicit that these things are quantum operators, that means this. So what is this? Well, it's u times e to the minus I p dot x O of 0. And to figure out how this works, how this acts, we should take this combination of charges and find a decomposition of it in the following form. So first, exponential of a bunch of p's, then exponential of some d's, then m's, and then k's. And then O of 0. Okay, so this thing is just some element of the conformal group. And I claim we can always write an element of the conformal group in this form. First, we act with a bunch of special conformal generators. So there, it's pretty easy to figure out which ones we should act with. We just ask, this element of the conformal group, which point does it take to infinity? And that will tell us exactly what to put here, because k is the only thing that can move infinity. Basically, just kind of following that logic, you can show, you can convince yourself, if you have an element of the conformal group, you can always get it by first acting with k's, then acting with rotations, then acting with dilatations, and then acting with some translation. And the reason all these parameters are functions of x is just because the group element that we're decomposing is a function of x. The way you should read this formula is just that the conformal group element corresponding to u takes the point x to the point x prime. Why is that? Well, these things all fix the origin. So if we ask what the image of the origin is under this whole transformation, it's x prime. So the equation says that if we first translate to x, then act with a conformal generator, that's the same as translating to x prime. Okay, so this is a way of saying that the group element in the conformal group corresponding to u just takes x to x prime of x. Okay, so this decomposition exists, and if we can find it, then it's easy to see how what this expression is. The reason is that k kills O, so that just becomes 1. Here, m acts in a finite dimensional representation of O, so we can just replace m with minus s, where s is now a finite dimensional matrix. We can replace d with I times delta. And then we have this thing as what? So e to the lambda of x delta e to the I omega dot s O of x prime of x. Okay, so if we can do this decomposition, we can immediately see how this thing acts. So now we have to ask sort of what are these lambdas and omegas? And I won't prove it, but maybe you can convince yourself that lambda and omega are given by the following. So this is something I'll call capital omega and let me put explicit indices on everything, SOD indices, where these quantities are defined by the Jacobian of this conformal transformation. Well, not the Jacobian, the matrix, the derivative of the conformal transformation. So a conformal transformation has the property that if you take its derivative, that's a product of a scalar factor times an orthogonal matrix. So this is orthogonal. And what I mean by this is just the action of this orthogonal matrix in the appropriate representation that O transforms in. So for a scalar operator, R of O would be 1. For a vector operator, R of O would just be O. And so on. Okay, so in principle, this is how you do the computation, and this is what the answer turns out to be. And the only thing I want to emphasize here is it's, again, completely determined by the condition that O is a primary. Okay, so there's a computation that I haven't completely done, but these conditions tell you, in principle, how to do it. Yes?
Can you find that decomposition by just writing the general element group and using computation in that form? Or?
Yes. So great. So another thing you can do that leads to the same answer is to say, OK, let's write our group element as exponential of some charge. Now we know the differential operator that the charge acts by. So we know how k acts, and we know how m acts and how d acts. So we exponentiate those differential operators, and that gives the exponential of a differential operator in general gives some diffeomorphism, and that's x goes to x prime, and then there'll be additional pieces that come from the terms like delta and s and that sort of thing, and those will lead to this extra stuff. So that's totally another completely valid way to do it. Good question. So okay, so the upshot is that the action of a finite conformal generator on a primary operator is given by some scale factor, some action of SOD, and some translated version of that primary operator. And again, this is in a particular quantization of the theory. This is conjugation by some unitary operator. Great, so that's my handwriting being a problem. So yeah, I probably shouldn't have chosen O for the orthogonal matrix. Maybe I should pick a different letter. Letters? Anyone? Oh, we already have R. That was the first thing I thought of. W, great. Okay, that's a great choice. Okay. So hopefully this removes all ambiguity from the formula. Okay. So we could have started with this, actually, and a lot of conformal field theory courses do start with this relation, but it's a little unclear where. I mean, it's natural enough looking in this form, but the point I want to emphasize is it comes from the algebra of symmetries and the structure of the conformal multiplet. And this will be important for us later. But this formula is great because we can now start to do a lot of computations. So let's start looking again at correlation functions. Yeah. Thank you. Wow. Good. Yeah. So thank you. Yes. That was a major typo. It was O before. It wasn't 0, it was O. Okay, that makes sense. Good. Okay. All right. So you may remember once we had the action of scale transformations, we were able to say what a two-point function of operators that were eigenvectors under rescaling. We were able to say what this two-point function was. So I'll just remind you. So we derived that this is some constant over x1 minus x2 to the delta 1 plus delta 2. So this is in a scale invariant field theory. But for a CFT, we have stronger conditions. There are two paths that we could take for understanding CFTs. One of them is the following. So to derive this, I demanded that when you act with the dilatation operator, when you act with the dilatation operator on both operators, then the result should be 0. And the action of dilatation was given by this differential operator. So I had a sum of the differential operator at point 1 plus the differential operator at point 2 times this thing had to equal 0. So I demanded that d acting at point 1 plus d acting at point 2 times this thing had to vanish, and that's what led to this equation. So the natural thing to do if we have a primary operator is a two-point function of primaries in a conformal theory is we should demand the same thing for the action of the special conformal generators. And I'll leave it as an exercise to do this. By imposing that this equation equals 0, you should find some additional constraint on the two-point function. And I'll tell you what the answer is because we're going to do it in a slightly different way right now. But this is a straightforward thing to do, and I recommend doing it. Okay, so instead we're going to use a finite conformal transformation because it's just slightly more convenient for what we need. So what should be true? It should be true that if we have a correlator of a bunch of operators in a CFT, and let's think in path integral language for fun. So we have a bunch of operators like this. If we have conformally invariant boundary conditions at infinity, then it should be the case that if we insert u, the exponentiation of some conformal charge, then it leaves this invariant. But of course, as usual, we can deform this so that U acts on each of the individual operators. This should be the same thing, just using the fact that U is topological. So that means that this correlator is equal to the same thing that we would get if we acted with this finite conformal transformation simultaneously on all of the operators. And I wrote what that formula is over there. And I'll just write that I'll specialize to scalars for the moment. Okay. Good. Okay. So right. So this is an additional condition that our two-point function has to satisfy. So let's check whether it's satisfied. To do this, exercise, show that under a conformal transformation, the distance between 2 points transforms in the following way. So it transforms to the distance between the conformally transformed points times some overall factors. This might look a little bit strange. When Joao teaches you the embedding formalism next week, it will become totally clear.
Did you check which one that he's going to explain the embedding formula?
Oh yeah. Oh yeah. Yeah. I'm going to keep mentioning it. I love the embedding formalism. I'm sad that I'm not lecturing about it, and you will all love it too. And if he doesn't tell you about it, then you can punish him. Okay, so a hint. It suffices to check inversions. So inversions take, again, x mu to x mu over x squared. Why? Well, first of all, this equation is obviously true for translations and rotations, where omega is just 1. And it's also true for rescalings. So you just have to check it for special conformal transformations. But a special conformal transformation is an inversion followed by a translation followed by an inversion. So if it's true for inversions and translations, then it's true for special conformal transformations. So check for inversions. Good. Okay, so using this, we can now look at our scale invariant two-point function. This is x1 minus x2 to the delta 1 plus delta 2. What is this equal to? Well, using this equation, this is omega of x1 prime to the delta 1 plus delta 2 over 2, omega of x2 prime to delta 1 plus delta 2 over 2. C, our constant, x1 prime minus x2 prime. Okay. And how does this compare to the conformal word identity at the top of the board? This one. What's that? Well, is it the same?
All deltas should be equal.
Yes, exactly. Good. So this is consistent with this. So let's call this thing Bob. So this is consistent with Bob if delta 1 equals delta 2. Okay, so the conclusion is we can say something slightly stronger about 2-point functions of primary operators in a conformal field theory. It's not just true that their 2-point function is given by a power of the separation between them. It also vanishes if the operators have different dimensions. Okay, so just to write it explicitly, 2-point function of O1 with O2 in a CFT is some constant Kronecker delta. This notation just means it's 0 if delta 1 doesn't equal delta 2, x1 minus x2 for the 2 delta 1. Okay, so this is for a CFT with primary scalars. And you can check that right, okay, so yeah, and I hope you all do the exercise where you recover the same result using the differential operator for k. You should find the same thing. So it turns out that conformal invariance also fixes 3-point functions of scalars. And I'll just write down the answer for you, and it will hopefully be clear that it satisfies the conformal word identities. So basically, this is also just a product. So there's some constant f1, 2, 3 over a product of powers of the separation between the different points. So I'll define xij is xi minus xj. Xij mu is xi minus xj. And when I just write it without a mu, I mean the absolute value. So delta 1 plus delta 2 minus delta 3, x23 delta 2 plus delta 3 minus delta 1, x31 delta 3 plus delta 1 minus delta 2. Okay? And please convince yourself that this, using the exercise above, satisfies the conformal word identities. And in fact, it's the only thing that does. So this is great. This is probably something that you've heard before, that conformal symmetry is powerful enough to fix all 2- and 3-point functions in the theory up to constants. But the story for 4-point functions is different and more interesting. So for 4-point functions, there exist combinations of 4 points that are conformally invariant. So these are called conformal cross ratios. And they're usually defined like this. U and V is just U with 1 and 3 swapped. Okay, and using this exercise above at the top, you can see that these combinations of the 4 points are invariant under conformal transformations. And so what this means is that a 4-point function, say of identical scalars, so instead of O, I'll call them phi, just for fun. can now be equal to some function of the conformal cross ratios divided by powers of separations. And for an arbitrary function here, this expression will be consistent with the conformal ward identity at the top. And so, have people seen the conformal cross ratios before? I know some of you have, but they're mostly familiar. So do you know why there are two of them? Should I go over that? Yes? Okay, good. So, okay, so why are there two cross ratios? So if you imagine you have 4 points, then you can start using conformal symmetries to move them around. And the typical thing to do is to put x4 at infinity. So we just use a special conformal transformation, a translation around infinity, to move x4 to infinity. That we can do. Then we use a translation to put x1 at the origin. Then we can use a dilatation and a rotation to put x3 at the point 1, 0, 0, 0. Without moving x1 and x4. What's left? Okay, so now we can now what we can do is we can act with we can't act with dilatations anymore because then we move x3. Can't act with translations or special conformal transformations because then we move x1 and x4. The one thing we can do is act with rotations that preserve this line. So the final step is we can set x2 equal to x comma y comma 0, 0, 0. Okay, so by using the conformal group, we were able to completely fix the positions of all 4 points up to 2 independent numbers. And x and y are conformal cross ratios, they're conformal invariants associated with the 4 points. And conventionally, we define z as x plus iy. And you can check that u and v are just functions of z and z bar. So u is z bar, and v is 1 minus z, 1 minus z bar. And this is easy. It's just because u and v are conformally invariant, so we can evaluate them here with this particular configuration of the points, and you'll get this formula. Okay, so that's why there are two cross ratios. And our 4-point functions can depend on them. So this this function here, as far as that word identity goes, can be completely arbitrary. There are a couple constraints on it that we can see immediately. So one of them is that this correlator is manifestly invariant under permutations of the 4 points. If you like, you can think in path integral language, where you just have these operators inserted at these 4 points. There's no sense of ordering or anything like that. It obviously doesn't matter. It's the same object in path integral language. And in some quantization, it's because of the time ordering. Okay, if you change the order of the points, the time ordering will just reshuffle them back. But this thing is not manifestly invariant under permutations. So in particular, you can get a few constraints on G. So by swapping points 1 and 3, you see swapping 1 and 3 swaps u and v. And if you keep track of these prefactors here, you get a constraint that g of u and v is u over v to the delta phi times g of v and u. So that's one thing that must be true. And then, so that's from swapping 1 goes to 3. And you can get other constraints. G of u and v is g of, I always have to look at my notes for this one. In fact, I think I might have gotten it wrong. Let's see. We're going to swap 1 and 2. So swapping 1 and 2 takes u to u over v Yeah, okay, I got it. Right. Okay. So this is from swapping 1 and 2, or 3 and 4. And all the other, and these swaps generate all the other permutations of the 4 points. So from permutation symmetry, you get these constraints on G. And this first one will be our favorite equation ever. It'll play a major role in what follows. Any questions? All right. Okay, so I should also mention operators with spin. And here the story is very similar. I'm not going to do any computations, but just write down the answers. And the reason I'm not going to do any computations is because Joao is going to teach you the embedding formalism, and then all the computations will become completely transparent and practical, and anything that I would do here would look totally stupid. So I'm not going to do them. But I'll just show you. So conformal invariance fixes a 2-point function of operators with spin entirely. So as an example, a 2-point function of vector operators has this form. Where this tensor I mu nu is completely fixed. And again, the 2-point function is constrained to vanish if the operators have different dimensions. And actually, 2-point functions, I should say, between operators with different spin are also constrained to vanish by conformal invariance. So as an exercise, if you like, you can check the conformal Ward identities for this 2-point function, and I recommend checking them in this form. It'll be exactly the same as the check we did for scalars, except you'll have to keep track of this rotation matrix. Okay, but the hint is the same. It suffices to check for inversions only, and you should convince yourself of that too. Yes?
There's a factor of 2 there, no?
Thank you. That's extremely important. Factor of 2. Without it, that check wouldn't work at all. Good. And part of the reason that that everything works is that I mu nu. Well, let me raise one of the indices. This is just W mu nu over there for inversions. And that explains, well, that's one way of interpreting the factor of 2. Inversions, basically the orthogonal transformation associated to an inversion flips the radial direction and leaves all the others the same. So this thing had better be a matrix that has one -1 eigenvalue in the radial direction. So that's eigenvalue 1 minus 2. And then all the other eigenvalues are +1. So that's what's going on there. Okay, so you can check that. And the answer for more general operators with spin is just given by a bunch of these I factors. So if we have more indices, J mu1 through mu L, nu1 through nu L, then here you just have a product I mu1, nu1 of x minus y through I mu L, nu L of x minus y. And you should demand that your operators transform in irreducible representations of SOD. So in particular, we should demand that this be, in this case, for example, we could consider a traceless symmetric tensor. And then what you should do is take this expression, symmetrize it in all the mu's, or all the nus, and subtract all the traces. But you'll get a unique answer starting from this. Okay, so the 2-point functions are completely fixed. And 3-point functions are fixed up to coefficients. In general, if you have a 3-point function of a bunch of operators with spin, then there can be a finite number of coefficients that can appear. So there's not just one structure, but there can be some number of structures that depend on the spins of the operators. In the case that we'll care about here, which is just a 3-point function of 2 scalars with the spin L operator, there's just one structure that can appear, and it has the following form. So it's just something that I'll write in a moment times the scalar piece. So by this, I mean the expression for the scalar 3-point function that I wrote over there on the board, x ij's to different powers. And this z mu is x13, x23 over x12, x13 mu over x13 squared minus x23 mu over x23 squared. And again, this looks a little bit out of the blue. There are some nice ways to derive it with what we have here, but the embedding formalism is the best, and you will learn that next week. Good. So that's all I'm going to say for now about conformal kinematics and correlation functions. Are there any questions? Yes. Pardon? Oh yeah, that's a great question. So you can have spinor operators. You can have operators in really arbitrary representations of SOD. And conformal invariance fixes their 2-point functions exactly. There's just one 2-point structure that can appear, and for 3-point structures, there is always a finite number of 3-point structures, and it depends on the representations how many there are. But yeah. Yeah. So you can try checking the conformal ward identities for this, and you will succeed, but it won't be fun. Other questions? Yes. Yeah. Good. Okay. So we could put it there. So conventionally, what we do is we actually normalize the operators so that C is 1, and that is what we'll do for most of this course. But yeah, conformal invariance doesn't fix the C, and actually. Sometimes it's a good idea not to normalize the operators so that C equals 1. An example is when the operators already have a natural normalization. And an important example for that are conserved currents and stress tensors. So they inherit a natural normalization from demanding that they satisfy the appropriate ward identities. The ward identity would change if you rescaled the operator. So once you write your ward identity, that determines how the operator is defined, and then the constant that appears here is not convention dependent and actually has physical meaning. So the example is C that Juan talked about this morning, the central charge of the theory. He wrote it as the coefficient of a two-point function of stress tensors, and that has meaning because the stress tensor has a canonical normalization. Good question. Others? Okay, great. Okay, so I've been writing a lot of commutation relations and saying very confusing things about how when I write a commutator equation, I mean that it's true in any quantization of the theory. And it seems like I'm belaboring this point to a weird extent. But now we're really going to have fun with it. And the reason is that in a conformal field theory, well, in general, it's a good idea to pick quantizations of your theory that respect symmetries. You've seen two different types of quantizations so far. One is the usual quantization where you pick spatial slice and some time direction and you evolve. That's a useful quantization in a theory that has translation symmetry. The other quantization that you've seen in Juan's lectures is a quantization where we think about states living on these kind of half spaces, and then we evolve them with rotations. That's a natural quantization to use in a rotationally invariant theory, or in Minkowski signature Lorentzian invariant theory. In a CFT, we have extra symmetries, and it's natural to use quantizations that respect those symmetries. And the one that's the most awesome is a quantization that respects dilatation symmetry. So instead of cutting the path integral on some spatial slice and evolving in some time direction, we can cut the path integral on spheres surrounding the origin. And we can talk about states living on those spheres and evolving from one sphere to another using the dilatation operator. So field configurations on SD minus 1 span a Hilbert space. We evolve in this space with e to the I d times tau, where tau is some time parameter, some dilatation time. And we can act on these states with charges by inserting Q on these spheres. Topological surface operators supported on the sphere. In radial quantization, there is the map between path integrals and time-ordered products looks a little bit weird. So usually this thing gets interpreted as a time-ordered product with respect to whatever time. Yes?
It's a little small.
Ah, okay. So if we have an expectation value of a bunch of operators, then we can interpret it in the usual way using the usual kind of time evolution, but we can also interpret it in radial quantization in terms of some overlap of states with a radially ordered product of quantum operators. So here I'll be extremely explicit about these things being operators acting on a Hilbert space. And I haven't yet defined what this state actually is. This thing lives in our radial quantization Hilbert space, but I'll define that in a moment. This radial ordering means that we order the operators, so we can think of these as matrices acting in the Hilbert space, and we act with them in an order that's given by their distance from the origin. So this is a theta function that says that the point xn is farther away from the origin than xn minus 1, and so on out to x2 minus x1 times a particular ordering of the operators plus permutations. And as is usual with these kinds of things, this looks like a totally weird and funky expression. Why would you have theta functions? Why would you have permutations and so on? Whereas this thing looks nice and beautiful and respects all the symmetries. But everything will be consistent, and I'll try to show you some examples of consistency conditions between these formulas later. Okay. I don't know if it's okay, but would it be possible for me to take a little bit more time than? Would it be okay if I went on a little bit longer?
Sure.
Okay. I have a fair amount more that I wanted to say, but I'll just try to get to a natural stopping point.
A possibility is to let people have coffee.
Oh, okay.
And then we could come back. Do you have other plans for the discussion? So.
All right. I want to keep going. I feel like we have momentum. That's right. I feel like we have dimension as well. Good. Okay, so radial quantization. What are these states that I'm talking about? So, for example, what is this zero state in radial quantization? So there's a simple way to get states. Which comes from operators. So the simplest state that you can define in pictures is just the path integral over the interior of a ball with fixed field configurations on the boundary of the ball. Okay, so this is the kind of language that Juan has been using. You use a path integral to prepare a state. So here we're using the path integral over the interior of the ball to prepare a state on the boundary of the ball. And let me write that extremely explicitly since it's very useful to see. So this will be a sum over field configurations that are just functions of a direction on the sphere. So n is a direction on SD. For each field configuration, we have a state. And these states will be weighted by the path integral over the interior of the sphere with a boundary condition. So the boundary condition says that, so here we're going to do the path integral over all phi everywhere inside the sphere with a boundary condition that phi on the boundary of the sphere equals phi naught. E to the minus s of phi. S Euclidean. Okay, so hopefully you've all seen this kind of construction before, but I just want to be completely explicit about what this is doing. These are states associated with the Hilbert space on the sphere. They're field eigenstates, and we're taking this particular linear combination of field eigenstates. And that's what I mean by this picture. Okay, so there's a more general thing you can do, which is you can define a state that I'll call O of 0 acting on 0, which is to do the path integral where you additionally, actually, I'll do something more general. You do the path integral where you insert O of x inside the sphere and then do the path integral. Okay, so this is the same thing, the same expression, where here we would put O of x. Yeah, in this language, this is just the unit operator, the path integral with the unit operator inserted. Okay, so anytime you have a local operator in the theory, you can create a state on the sphere. Yes? Great question. Let's show why it's a natural state to use. So what you said about evolving for infinity in Euclidean time will absolutely be true, and you'll just have to wait a few minutes to understand why this thing doesn't look very infinite, but why there's an infinity that's snuck in there. But here's something much more explicit that we can do.